I haven't said anything yet. Well, welcome everyone for a wonderful talk today from Professor Roland. It's coming from St. Ireland. He is a titan in astronomical instrumentation. You would say that he's been very instrumental. Shouldn't have used that word, instrumental. He's been really pivotal in developing optical instrumentation, particularly when it comes to integral field spectroscopy. Did you actually coin that word?
Yeah.
There you go. He coined the word. He built the first integral field spectrometer in the 80s. He mentioned earlier today. And then he went on, worked on a few other spectrometers, particularly, for the study of extragalactic astronomy, galaxy evolution, and built MUSE. He was the PI of MUSE, which it's probably the most heavily oversubscribed instrument out there right now. I think it's more than JWST. So it's truly a phenomenal instrument. And now he's looking forward beyond extremely large telescopes towards massive spectroscopic facilities, and is leading the efforts in developing the wide field spectroscopic telescope, which is what he's going to talk to us today. Please.
Thank you very much. Thank you for your presentation. So it's my last but not least stop over my small Canadian tour. I've seen it will be the 5th university. The idea behind that is first to get you excited about such a project, and second to see if it can be something we can do in common on the long term. It's a long-term project, so I'm really pleased to see so many young people here, because it will be for this generation, and also the less young, but not for me. Okay, so this is a project which is in the concept phase study. It's a study which has been funded by European Union, and so the wide-field spectroscopic telescope is something that we are really. I should maybe speak more on the microphone. Really, we discussing for a while because it's something obvious that is missing in the global landscape of astronomical facility. And you will see in the moment, yes, so many synergy with other facilities, something really we like to do, because it can address a large fraction of the science we do and to all scales. And this is the motivation of the device. So it has been on many long-range program. It is in the Canadian long-range program. It is also in the Astronet European Vision. I think it was on the decadal survey as well. So it's in many because it's obvious we need something. Why it was not done yet? Because it's difficult and it costs. So ISO now, as the ELP is shaping, expected light is in 29, so soon. So really an impressive project. Start to think about the next. Because the ELT from the first idea to the first light in took 30 years. For this big facility, it's always a sort of task between 20 and 30 years. So we cannot think all them in a row. So when we have finished one, we say, oh, what's next? We need to do a bit thinking in advance. And it's even more important because these are billion cost facility. So you can be in one, difficult to do at the same time. So the fact we select that other than something else will have a strong impact of your community. And you better do it twice. That's why we are. So ISO in this, I suppose, this expanding horizon, try to shape what will be the next facility for 2014 plus. So after the 8. And our answer is well field spectroscopic telescope. I will try to convince you that this is needs to be done. So we have assembled a consortium that for the concept study of many institutes in Europe, plus the Australia, which is currently a strategic partner to ISO, and which now is in the time that we decide to become a full member. And becoming a full member means that you need to provide not only the operational cost, but some input cost, inter cost, like is needed to get access to all the facilities that were built in the past. And with the idea that large fraction of this cost could be in kind contribution. And what usually people want is that this money get back to their industry. And so, and the other aspect is that they have been doing spectroscopic survey for a while. And so they are keen interested both, let's say, politically, technically, and scientifically to be part of the research. So they provide effort. Of course, they are not paid like the so it's in kind. We have also a very large statistic, which is open. And you can become a member if you wish to follow what's happened, you have to participate in advice or currently 700 members. So we've been working since 2 or 3 years to try to figure what can be done. Can be done in terms of to be very ambitious, but still feasible. And we came up after a few iterations to this top level requirements. So we're building a facility. We're not building a telescope. And then later on, we're building a facility that we need to think all together into the budget we expect to have, how we can make something which is the most scientifically efficient. Doesn't mean I will be the best telescope or one one, it's the total process. So we have a telescope aperture which is 12 meters segmented, semi-limited, at least for the Mars, with a telescope field of view of 3 square degrees, and which operates in the visible and the infrared up to 1.6 degrees. And then there are 2 instruments, only 2, but quite quick. there is a MOS, a multi-object spectrograph, and an IFS interactive spectrograph. So the MOS has two modes. One is low resolution and one is high resolution. So the low resolution works as an extremely high 30,000, which is an order of magnitude bigger than what we can do now. And with the spectral resolution in 2000, and it gets the full optical range in one go. Then the high resolution is smaller multiplex, but very high spectral resolution, 40,000, which is quite challenging for such a big telescope. And of course, doesn't cover the full spectral range, but we'll cover 3 to 4 regions. Then we have one interactive spectrograph, which is much more field of view, but quite big compared to the existing one. It's 9.5 millimeters square, so it's 9 times mu, with a spectral resolution that is higher than what's directly used, and which also covers the full range of the case of news. So, and then there's a larger patrol field, I will come back to that. And then there's finally 2 operational requirements, which are quite important, and have a strong impact on the design, operation, is that the MOS and the IFS should run in parallel. And we will see this is something quite innovative for big telescope, and will allow much more science for the same cost. And we also want to implement target of opportunity, both at the telescope and at the fiber level from the start. And the reason is that we are convinced that time domain science will be very important in 2040. Because of all the other facilities. So that's the topic about it.
Can we ask questions?
Yeah, sure.
So the spectral range goes to 1.6 microns.
Yeah.
Is that to future proof it? Because these instruments don't go that far.
Oh, sure. I will answer your question in 2 slides.
Okay, thank you.
So, just to show the field of view, which is a characteristic of the telescope. So, big telescope comes with small field of view because of the conservation of étendue, the AO by the image. So, trying to get big field of view with a large telescope is very difficult. So, we try to push as much as we can. And 2 degree diameter for 12 meters is very tremendous. This is the most of AR. And this is compared to the VLT, which is only an 8 meter. And the ELT, the big one, 39 meters, but you see how small it is. And within that area, we can position all the 30,000 low resolution plus the 2,000 high resolution fiber anywhere, except in the real center. In the real center, this is devoted to the IFS. So there's 13 meters diameter, which is a patrol field, and with that you can position the IFS where you want. You can look to the size compared to news, which quite big. It's a huge instrument, but it's big. So it's much bigger. And the fact that you can position independently is very interesting. So while you are observing a field, you always are, because of the clustering of the sources, to make multiple configurations of the position, multiple exposure. At the same time, because it's fully independent, you can either do a big mosaic to achieve a field of view of 9 by 9 by 2 square, or go much deeper, or even follow a moving object. So this brings flexibility and having almost 2 instruments working at the same time, using the same architecture. So that's why it's very efficient. Then we have to see what science is doing, and we will come to that.
So just a clarification. The MOS can only go to those yellow region, cannot go to the white and the blue
No.
region. There will be a big hole in the center about 50 degrees.
So, yeah, so that will be, but in fact, the real hole you have is just the white. Because here, if you do a mosaic, you will get spectral everything. And usually you go faster with IFS and with the MOS, because it's more efficient. So if you are interested, I don't know, a certain type of galaxy, you will have it with the MOS, but you will have it also with IFS. So it's maybe only this area which is not covered. Then you can push it if you want complete coverage. So then the question, yes, it's obvious, we don't go to the infrared when the telescope is designed to be modified, because it's an upgrade plan, so we don't force it to go to the infrared yet. There is a reason for that. The reason is that currently we are building moons, which is an infrared MOS for the DLT. Moons will have 1,000 fibers. So to be competitive with that, we need much higher multiplex. Either 30,000, let's say 10,000. 10,000 will translate to a huge number of infrared detectors, which are very costly. The second point, more technical, is that we have to demonstrate first with moons or PFS that sky subtraction with fibers can be done efficiently to go deep enough. It's quite a challenge. And here, because it's twice the aperture, we need 2 times more difficult. So this is not a great plan for such a facility. The other is to add mini-FUs in the MOS. And we are thinking about using GLO for the FS. Probably, if it's feasible, we'll move the baseline. Something nice to have. So we can compare this facility in terms of numbers. So the usual way is to compare the MOS multiplex with the telescope aperture. And you see, so this is the present generation, this location. So DAISY, PFS, FORMOS, WIP, moons. Okay, so you see this is a typical type of multiplex aperture can do. And then there is the ELT one. So it's certainly big aperture, but small multiplex. The area of the circle is proportional to the étendue, which is in a way related to the surface speed. And you see the ELT will not be a strong player in that problematic. There will be fantastic differences. And then this is Spectroscopic, which is being discussed in the US, the forum of DAISY. There is a MOS, which is in construction in China, and the MSC, which is stopped. If it would have been done, it would sit there. And then you see, so it's fairly on the top. But the IFS, the panoramic IFS, the same here with the field of view, the telescope aperture and the étendue. And you see it's overwhelming compared to any other harmony, which is the small IFS for the LT, absolutely combined. And we have the combination of the two. That's, I think, really make unique such an instrument. And I don't think that any other instrument that is planning something. So how it looks like. So this is the telescope is an F1 cathedral, F1 mirror. It's based on the ENT segments because the huge spending has been done on developing the segments. So we use exactly the same, except of course for the prescription on the surface, but the rest will be exactly the same. And with secondary and which is 2.4 meter, which will do dictate or the needed correction. And then it is this light is sent to through a field corrector and an atmospheric dispersion corrector to the fiber position. So it will have H3, which is something for fiber. And then all the fibers are sent to the right spectrograph, the MOS spectrograph, which sits in the azimuth platform. And this is to limit the size of the fiber, which is especially important for the throughput in the. And while you're doing that, there is a small mirror here that send the light, extract the 13 arcmeter patrol field to through an MOS IFS relay, which can select the position of the 3x3 arcmeter you want, up to the good place where sits what we call the FS station, which is the youth number spectral. Now it's latest device 192. It has even increased. And so it is in a stable environment. And you see why it's a fertility. Because the size of the overall things is dominated by the need to put on this spectrograph. And the telescope is on this fraction. And you cannot do that in any existing facility. And you need to design from the start. So, as I said, it's a very large field, and you can compare to that as a matter of étendue. And in terms of the étendue, WST, the MOS, will be the highest étendue telescope, optical telescope ever built, even bigger than Roland and SST, and not bigger than ours. The second is what I mentioned, is a parallel operation. Operation is very so in terms of control, it puts some interesting things to do, but it's quite busy. And now we have finalized the design of the test, and we're pretty confident that it can be done. The positioner is a challenge. You need to put 30,000 fiber in an area which is not very big, because you are limited by the size of the largest lens you can put on the corrector, which is 1.6 meter. And then indeed that the fiber index and all the motors and so on actually need to put in a very small things. I think the pitch is currently less than 6 millimeters. Quite challenging compared to what we do now. So we're looking to various possible designs. So evolution of the tilting spine, which is the one which are used in Kidna foremost. See we can take like that. We are looking to the theta field positioner modules that are built by EPFL that are used in DAISY. But with much more compact motor and system. Then there is a very new design that called theta flexible positioner, studied by UKLTC, which one of the points of the positioner is you move them, but you need to keep them on the surface. So the principle is you need to be aligned, otherwise you will lose light. And so if you are allowed to motion in Z as well, it's better. And a very new innovative design, the PEX design by Bosnia, which is inspired by this system, flexible, which has been developed for medical purpose, when you need to put something in the eye to measure things in the eye, and it has quite a large patrol area, and naturally it can move in all directions. But it looks quite promising, pretty cheap. Spectrograph, well, many spectrograph, and you can see, so far, we have nearly currently, as the design is now, 230 spectrograph, each one with various arms. That leads to a significant number of detectors, nearly 500, And it's a significant number of gigapixel or wide exposure, which is 7 times LSS. So that's definitely a big data. The cost of the spectrograph is expected to be the major part cost of driver cost facility. So we try to minimize it as much as possible by doing various innovation. One is to use a curve detector. So curve detector, here you can see an example of the curve CMOS, which is done at Lyon in Marseille. So if you have every optical system you will produce a curve optical surface. So if you don't have to flatten that with the optics, you can simplify so much the optics. Less optics means much less cost and better efficiency. Again, control aspects. So this is a design here. Currently using curve detector, we have a backup which curve detector doesn't go up to the level where we go, but we are currently doing study with ISO and some real test. We have another design that's mostly for the MOS, which based on forward shoot camera, which can be extremely fast up to f.8. And allow to put the detector still outside. There is a problem that the detector is inside the system. Where this facility will be, so it will be an ISO facility. So we put in the best ISO sites, which are parallel and RCS in the south, which is a natural follow-up for an SST, SKO, Ministry South makes a lot of sense with that. And there's still a few peaks available. So in the region we have L'Aventura, L'Aquila, Montarones, and Maquena. These two are outside of the proprietary zone, so you can negotiate with the Chile. We look into L'Aquila particularly because it's within the property and it's also a good distance from the VLT and ELT, not to be a problem with the laser. All these systems have a lot of lasers, and of course, it will be a problem for us with the large laser confusion. The second aspect is sustainability. We cannot build a big facility like we've done in the past. We have to really care about the sustainability impact of our facility. So this is something we're looking very seriously. And then developing research, we have huge impact on infrastructure. Secondly, we can use the parallel solar plants as producing green energy there. We also look into various aspects of sustainability, like to have a very efficient cooling system with parallel spectral detectors. The cooling system can consume a lot of energy. So we're looking into that and all of it. So sustainability impact is part of the trade-off on the side. So with such a system, we will just to give you a few numbers, in just 5 years of operations, we can we have 300 million of galaxies down to great magnitude about the entire accessible south sky, 25 million of stars onto the entire galaxy as well. The higher resolution we get, of course, less a few million stars, but it is very hard spectral resolution, and that's also very interesting by science. And the IFS will produce 4 billion spectra over a smaller patch of the sky, but enough so to get statistics. That's what happens in this region in diverse environments like low density galaxy stars, matters, spaghetti. So what can be done with such a sample? Many things, many differences. And I won't have to cover all. It's very large. We have split into galactic and observatory population. It's like Ecotrolia and Panoramic. And I will give you a few examples of them. But before going into that, each of the science scales use a combination of these instruments. Usually, there's a quite a good, interesting things to do when you have the IFS and the MOS observation working together. And the other aspect that I would like to mention that the WST has an extremely strong synergy with ongoing or foreseen a large facility, the same scale. Having WST will enable new science from this facility. So we have, for example, with Roland SST, most of the time itself will require for spectroscopy. So don't have something which is like high-multiplex. So SST will produce millions of variable events. Down to extremely different only big telescope, which is a large multiplex, can do a reasonable follow-up. SEAO, you see that is a really short science case, and very strong signals. So if you have SEAO and the spectral information, then we can get more science. The other sciences are really very. Regarding science case, we have identified the main science theme, original element of the Milky Way system, the disk, the bulge, and the origin of stars and planets. In a way, we are starting to do this science with the present facility, like Gaia, hormones, moons, and wind. And it's sort of pathfinder, what can be done at a much larger scale with this. So the origin of elements, so we use high spectral resolution, so it's for 20,000, going to 40,000, which we managed to that, we much more access to other elements, but we can measure the abundance. And this allows to answer quite a number of interesting questions like the neutron capture element or the type 1 supernovae. And so that here the high spectral resolution is a key. So we are not going to observe extrasolar planet directly because it's not a machine able to do that, only to high spatial resolution. But still we can do very interesting science which is needed for this business. So in 2040, the expectation is that the combination of all this facility will have 100,000 planets or stars, which is quite a significant number, including a large fraction white flames. And then the question maybe not at that time to get more, but to understand better what is the link between the stars and the planet formations. So if we can get an homogeneous measure qualification of the stars, abundances, with respect to the stellar parameters, age, and galactic properties, depending where we are in the galaxy, and we try with this statistical number, try to link where preferentially the planet forms. The second aspect is to do systematic survey of the white dwarf metal polluted where there is a rest of planets that can be observed directly in spectroscopy. And we expect a large number to be found by SST that will be spectroscopy. So we can do something in that direction.
Are you gonna do any radial velocity measurements?
Yes, we can do radio velocity, but not to the precision to measure, to discover new planets. We can, for example, measure binaries, how much binaries they are. So there's more in that in this field, sorry. So the origin of the Milky Way, I see there's a few interesting things to do, is to measure radial velocity, metallicity at very large distance, and abundances nearby. And that's need to understand really how the galaxy form to varying the abundance of the elements to distinguish between different formation process. And what there is here is to extend what we're currently doing, will be doing with formals, obviously, but to a much larger scale. So this is where with the sun-like stars, that's what we do currently, and you see we extend that. And from the red giants, we go much further. So we go up to the halo. And I think this is something which is, I think, you're very important. For the results in our population, here we'll use the IFS because this is a relatively dense system. And we point the IFS on the local group graph galaxies. And then with because it's very big IFS compared to what we have now, we can search for example, the massive stars. We can do a complete census. This measure also the velocity and stuff. And that will allow lots of science, like study the role of ultra-faint dwarf in galaxy evolution, and to study the bionic dark matter properties. These galaxies are specifically sensitive to dark matter. And so we can do a lot. And then while the FS is doing the center, we can do on the external part, which are less dense, to the MOS to complete that at larger distance. Again, we need the two at the same time. The extragalactic size, many sciences, I will show a few of them with the epoch organization, the cosmic webs, galaxial network system, AGN black hole nearby galaxial. Don't have time to show everything. You can read that in the white paper. Here we show the epoch of realization because it's a good example of the synergy between SKA and WST. So the SKA law will study the 3D distribution of the neutron gas, hydrogen in 5 divisions. And they will have it in a sort of cube, of course, with covering a redshift band, which is interesting for the end of the end of radiations we can do between 5 and 6.7. And then at the same time, if we can do the spectroscopy of a whole galaxy in this range, up to a certain magnitude, but we need to go further. We can also measure their ionizing properties. And by doing the correlation between this population and what SKA will give, we can understand, try to figure out what are the sources of ionization, what are the scale of the ionized bubble. So,
what is the limiting magnitude that you are planning to go down to?
well, it depends of the hair. Probably we have to go to some depths. So I don't know by 2025, but I need to confirm.
Yeah. Okay.
There is a sciences which are found particularly interesting, because I will tell you back on that, because that's important in the time. It's to trace the cosmic web in a way that I've never been done. So here we plan to expand the exercise we've done with MUSE. With MUSE, we will be able to recover the Lyon alpha flux, which are around high-redshift galaxies, relatively easily for the first time. That trace what happened into the CGM, circumgalactic universe. It was very interesting to understand the behavior of a very complicated system in FAPS, where you exchange gas and expel gas from stars and so on. So it's very important to understand the galaxy. But here we wanted to go to another scale beyond the circumgalactic universe, to go to the intergalactic universe. But the scale where we can see, possibly for the first time, the filaments directly, doing direct imaging of the filament using the extremely fine glow of the Lyon alpha. This is what we did, and we were able indeed to find bits. You see, I made, I think it's the real data of the filament at the megaparsec scale, so much beyond the CGM scale. And it's very interesting, but it took hundreds of hours of exposure, so it's somewhat a unique experiment. With WST, which allows to access bigger pressure, lower redshift environment, and much bigger field with FX. We can extend that by doing a deep field exposure with the FS, but pushing with the mosaic to 35 convoluted bigger parcel. And then you will get a complete picture to a good scale of the filament structure. Okay. And at the same time, because you're spending a lot of time to do that, you will locate your fibers on the LBG galaxies. And from the LBG galaxies, you can recover by looking to the Lyon forest, the tomography, which allows to reconstruct again, but at lower spatial scale, for larger distance, the So we have a complete view. And besides that, we have all the galaxies, of course. We are very deep, so we have all the galaxies, including the very faint part. And then we can understand how the galaxies are fed into the world, right? How their properties depend on their location with respect to the world, where the spin, all this sort of thing. How the star formation depends also. And this we can do from Redshift 2 to 5. So it will be a very impressive and unique data set to understand the connection of galaxies with their environment. If we go to a bit lower redshift, here the idea is to get really strong constraint on the dark matter. For that, you need a high completeness survey of a large number of galaxies. Are we speaking of 10 million? Over a significant region of the sky, but not too sharp, but down to faint magnitude, so this answer your question 26. So if we do that, we'll be able to recover the dark matter distribution. So this is the dark matter distribution and the simulation. So this is here the light cone, and this is the one redshift slice at 0.8. And here you see what will be recovered by 4 meters, it's foremost on Wisdom. So typically this is what you recover. So you recover only a part of the distribution because you don't get on fancy down. Okay. And this is what you recover from an SST. SST will go extremely deep, it's not a problem. But the spectrophotometric redshifts are not precise enough that you can isolate the structure, measure the groups, and so on. And so it's only having the two, the depth, and the real spectroscopy that you can recover the full distribution. And for that, you can test the non-discipline paradigm, the evolution of the air mass, the growth of volume, and it's much more familiar. So, massive cluster in cosmology, the idea here is to do comprehensive view of the massive cluster in the universe. Euclid will provide you tons of this massive cluster. And here we put the IFS in the center. And the size is perfect for using the strong gravitational lens to get the constraint of the dark matter distribution. And then you can also use galaxies, do the wave frequency or measurement to get an idea of how the filament fed the cluster. So we have cosmology slide 5, cosmology survey. Not much time to spend on that. We can just discuss. We could measure neutrino mass, and for the first time, do a multi-field, compare multi-field and equation with single field, and time domain size. And here, I just skip because I'm really late. But there is just one example where you can get the electromagnetic counterpart of gravitational events that will be formed by a telescope or ESA. That you will follow with LSST. LSST will provide thousands of events, and only the spectroscopy with WST will able to tell you which is economic counterpart. Again, it's measure. There's many operational challenge. Probably the most challenging part is not the telescope, possibly the instrument, but certainly the operation. The operation will have to work hard to make sure that such a facility can really provide the science. I think we are in good shape. We are doing that with a number of big data in the facility like the feed, like Gaia, will soon with the scale. So we'll do it, but we need some work because it's not only big data, it's complex big data. Data cube, spectra, not just images. And the only things you can be sure when you have things to predict the science in 15 or 20 years is that you'll be wrong by some parts. It always happens. And this is the fun, and this is why we're doing this facility. And so you have to think about what is the discovery power of the facility you want to push. So what is the discovery power of WST? Well, there is three aspects. Discovering of the MOS, because you select source, so this is the power of numbers and homogeneous data sample. We have learned, and good example is SDSS, that having a large homogeneous sample allow to discover things that were hidden in smaller samples. And there are a few examples like that. SDSS has produced 10 million galaxies in all its life. We produce 300 million in just 5 years. So I would be surprised if there is no discovery that this same for stars. The IFS, it's a different beast. It has no preselection, so it has a high discovery power. And this is demonstrated by the fantastic success MOS publication that published almost 35% of the population of the BLT now, even by news. And the reason is that first, it's a good instrument, I can say that, but secondly, it's very rich of information. Data cube that you've been using for doing something contains a lot of information that can be used for other sites. And this is clearly what happens, helps to the communication of. No reason it should be different, that the IFS obviously will be much larger than yours. So we just compute the number of, let's say, resolved pixels for voxels in 3D. The discovery power should be proportional to that. It will be 50 times the one of MOS and 90 times around the IFS. There is a high discovery. And finally, because it's built on the start, we plan to do WST as a discovery spectroscopic time domain machine. So SST will be imaging time domain, but there are some events where there's time domain event that show in line, shift, border, which appears, disappears, and so on. This is fairly well unknown currently. And for the first time, we will be doing systematic observation that will be split to allow this in this big sample. Also, I think there is a big discovery point. So there is a project timeline. I will be very quick here. We are just going. You just have to remember the important thing that we have a full proposal to send to June 27, and the year after, we shall know if this facility will be the next facility after there. And now, the two most important slides from my talk. So what was for the Canadian astronomical community? So remember the statistic, you can do it right now, it's over, wherever you can contribute, but I won't give you access, privileged access to the facility. For that, there's two paths. The first one is to become a strategic partner of WST, which will be involved in construction and operation phase, and then you have privileged access as a member of the WST consortium. But the most interesting part is to become a full ISO membership. If you become full ISO membership, then you have immediately in one click access to all ISO facilities, DLT, ELT, and WST. And the joining fee you will have to provide can be provided as a kind contribution to the WST construction. So that will help to channel the money back to the country. So in general, government are more happy if that's the case. And the second point is that by joining from the start a new flagship facility, you were able maybe to shape it according to at least to discuss within the consortium what you want to do. And secondly, yes, you build something which is direct strategic interest for your community, which is of course great. And then I see some additional reason to join us on this exciting project. As we have shared long and successful of history of CFH, it's been at the forefront of science at the time. It will be a pity not to continue, especially because we share technical and scientific expertise. And we don't know what will be the fate of the CFA, but at least on the European side and the French side, we are moving all the effort towards ISO for obvious reasons. I think maybe more subtle, but I'm very convinced that it's the way we do science is very simple. Maybe not exactly the same way than in every communities. And I have felt by own experience, like collaboration, that it's very important that to share the same way of doing science, the same way to collaborate. At ESO, you will be a strong partner with equal right to all the other major European partners. Not anymore a small and a large. And ESO is really world leading, and it's very leading, but most importantly, the most stable ground-based astronomical organization for long. Big project that takes a long time is becoming more and more. And unfortunately, like I said, to join an ESO flagship from the start, arise only every 2 decades. So it's a good opportunity now. Don't miss it. Thank you.
We have probably time for 1 or 2 questions. And then there's gonna be refreshments later. Yes.
Great talk. I was curious, since 2040 is a long way away, as you said, what's the biggest roadblock or the most likely thing to stop this from happening?
In terms of feasibility, I think it's much less difficult than ELT. So if we succeed on ELT, that's a good challenge. The funding is significant, but we have pushed the funding to a part that will be also less expensive than ELT, because we acknowledge that the economy is what it is now, and so we want to dream, but not too much. So I think in all aspect, I think it should be quite feasible to do, and yeah, I don't see major problem here. Just that there will be something on the road, of course.
Okay, thank you, great talk. So that's the WST has the science camera, like imaging the full field view.
No,
Okay,
no, we're planning maybe to have a small telescope side to do a monitoring. Because at that time, you will have high quality image all the time. SST,
okay,
Euclid, another facility. So it's not really good. So we may have a small photometric telescope just to follow things happen in the sky next time.
All right, let's thank the speaker again. So there'll be refreshments in the lounge.